Okay, we'll just wait for a minute and get started.
Sure, sure.
Mhm. Okay, we'll go ahead and get started. Thank you everyone for joining us for our webinar, the first webinar in 2025. And today we have Dr. Chirag Gupta from University of Wisconsin-Madison. He's going to be presenting to us on his research, which is focused mainly on wide bandgap and ultra-wide bandgap. He definitely brings a lot of knowledge, both from industry and research in the higher education. So Chirag, you can go ahead and get started.
All right. Thank you for the introduction. Let me.
Just one more information, I'm sorry. If you have Q&A questions while Dr. Gupta is presenting, please go ahead and type your questions and we will get to that at the end of the presentation. Thank you.
Okay, is my screen visible and my audio is okay?
Yes, it is.
All right. Should I get started or should we wait like few more seconds?
You can get started.
Okay. Hello everyone. I'm Chirag. First of all, thank you to Power America for the opportunity to share my groups and my work here at UW-Madison in the power electronics area. So for the lack of better title, I think what I'm going to talk about today is the wide bandgap and ultra wide bandgap material and device work that we have been doing over the past 2-3 years at Wisconsin-Madison. And the work that I'm going to present today is supported by National Science Foundation, ARPA-E or Department of Energy, and then we have industrial consortium in Wisconsin, which is called WEMPEC, Wisconsin Electric Machines Power Electronics Center. So basically we have some support from that, and then some industrial partners also are supporting this work. So all in all, we have efforts going on both wide bandgap and ultra wide bandgap, and the material that we have expertise as well as the material system that we work on is primarily 3 nitrides. We have some work in gallium oxide area, but primarily our focus is on 3 nitrides material, where we use GaN for wide bandgap, and we use aluminum gallium nitride channel and barrier materials for ultra wide bandgap.
Excuse me.
So, yes.
Oh, I'm sorry. I thought your slides weren't advancing. I apologize.
Okay. All right. So let me start with my introduction. So I got my PhD from UC Santa Barbara, the beautiful campus of Santa Barbara, where I worked on vertical gallium nitride devices, where my focus was on developing 1200 volt power transistors using vertical GaN. I spent 1 more year in Santa Barbara, as I wasn't able to leave that place easily. So I did a postdoc with Professor Mishra there. And after that, I moved a bit north to the Bay Area, where I worked at Maxim Integrated for a couple of years, which around the time I was leaving got acquired by Analog Devices and now known as Analog Devices. So I joined Wisconsin-Madison about 3.5 years ago as an assistant professor, and currently I'm in that position. So the work that I'm going to present today is from my research group, but it's building upon collaborations with material scientists, and I would like to give a shout out to 2 main collaborators. One is Professor Shubhra Prasad at UW-Madison, and Professor Asif Khan at University of South Carolina. I've been very fortunate to be able to get the material needed to make transistors that I'm going to show today, and to collaborate and to influence the device design. So the team that I have at the moment is I have 8 PhD students and a few masters and undergrads. So all in all, with focus on different areas of research. So today my focus is, at least in this presentation, is on power electronic or power semiconductor devices. But in our research group, we also do a little bit of optoelectronics and high frequency or radio frequency applications. So the work that I'm going to show today would not have been possible without the equipment and facilities on UW-Madison campus. So the couple of machines that we have here, one is a 4-inch Extron reactor, and one is an Agnitron 2-inch reactor. With both these reactors, we have the capability to do all kind of alloys of gallium nitride, and then we utilize the clean room on campus to fabricate on the material that we deposit at Madison. And currently we have measurement capability up to 3 kilovolts. We are trying to expand that. And as I mentioned before, our work is supported by this consortium, which is WEMPEC, and I'm an affiliate member for that. So with a little bit of introduction, let me dive into the research that we have been doing for the past 2 years. And I've broken it into two main areas. One is the GaN or wide bandgap related research, and the other is ultra wide bandgap related research. So in the wide bandgap space, our recent focus has been, while we have been working on the vanilla HEMTs a little bit, but I thought for this community, especially with industry, people from industry being around, I thought it might be interesting to share our recent efforts on bidirectional transistors and what we have been doing in this area. And here our collaborators are Professor Shubhra Prasad, who provided the material for this research. So what are bidirectional transistors and why are we interested in that? So bidirectional transistors are very similar to unidirectional transistors in some ways. And another way to envision a bidirectional transistor, if you haven't heard of those before, is they have the ability to block and conduct current in both directions. It's a true 4-quadrant switch. So you can get current in different ways depending on the application and depending on your needs. So one of the examples, and these bidirectional transistors are not needed everywhere. Like, for example, the unidirectional transistor or the conventional transistor with gate, source, and drain that we are all aware of, they are ubiquitous. But these bidirectional transistors, they have certain applications and they have certain topologies where they provide extreme advantage. And some of those, as you can see here, like as an example, as I learned recently, that these are great for AC-AC conversion, because 3-phase AC-AC conversion, because it allows reduction of the total number of transistors significantly. So if you would do it with conventional transistors, you may need 36 transistors, but if you use bidirectional transistors, which allow blocking and conduction of current in both directions, you can get away with 9. And the other advantage is the DC link capacitor. So here, this DC link capacitor can cause some issues. So basically, you can also get rid of that. And it's always advantageous if you can reduce the form factor. It allows for numerous advantages that we have seen with conventional transistors. Now, this is one example. There are other places where community believe bidirectional transistors can bring in immense value. Some of those are matrix converters to support bidirectional power flow. It's not a necessity, but having that gives you an option. Then solid state circuit breakers, where you may want to block voltage in both directions or both positive and negative swing. The other is current source inverter, and this is something my colleagues at Wisconsin-Madison have been working on for quite some time, is to use current source inverter instead of voltage source inverter for variable speed motor drive. So all in all, at least as a device engineer or as a semiconductor person, this seems like an exciting topic where these transistors have a reasonable amount of applications, and when I look at the literature compared to conventional transistors, these haven't been explored in that great detail. So this was something that that I started thinking about a couple of years back, and we started working on this. So, so how do people implement it? So there are different ways of implementing it. If you don't have access to a bidirectional transistor, I think until last year, there were no bidirectional transistors commercially available. Recently, they have become commercially available, or at least they are going to become commercially available very soon. And when I say like the voltage range I'm talking about is 600 volt and or at least 200 volt and beyond. So the way people realize these bidirectional transistors or equivalent functionality was through the series and parallel configuration, where you just take two transistors and two diodes and you connect them in such a way that it starts to behave like a 4-quadrant switch, or depending on whatever you are trying to do with that. While that serves the purpose, but it's not an ideal solution, because now to do the job of one particular device, you need four. There are contact resistance, you have to connect them. It makes it complex. It increases the cost, reliability goes down, you have more parasitics in there. So all in all, you start to wonder whether it's worth doing all this or not. And this is one of the reasons why these transistors, or basically bidirectional transistors, haven't really been explored in as great of a detail as they would. Another reason is beyond the complexity. If we get rid of the complexity, the other part you can see is that there is a good chance you'll get some resistance penalty. You'll have 2x, at least the 2x the amount of resistance as of a conventional transistor for the same rated voltage. For example, for a 600 volt, if you have 10 ohm part, if you take two transistors, you might have 20 ohm or even larger. And this is again not ideal, because in order to get the bidirectional blocking capability, we are paying that extra resistance penalty. And all these reasons, in my opinion, they don't make it very attractive solution. However, in this regard, I think gallium nitride is extremely suitable. And when I say gallium nitride, by that I mean lateral transistors are suitable for this particular device, which is monolithic bidirectional transistor. Potentially, it can be realized in silicon as well. But our focus is on gallium nitride. And one of the key advantages that you can get is, of course, you can get rid of all the circuit complexity, all the parasitics, and so on and so forth. But beyond those advantages, there is some inherent advantage that you can get from lateral transistors if you try to make a monolithic transistor, is that instead of getting those penalty of 2 times the resistance, the penalty you are going to get is little bit less. So for example, if you have 600 volt, 10 ohm conventional transistor, maybe you can get away with 600 volt, 15 ohm part instead of 20 ohm part. So this this to me was very exciting. That and the question as a researcher that I'm very interested is, it can I someday, can I by sustained efforts, can I make it 1x or 1.1x, like with absolute minimal penalty? Can I provide the bidirectional blocking capability for free? Spoiler alert, I don't have the answer today. I'm still looking into it, but this is the key advantage of gallium nitride, at least in my opinion, that gallium nitride brings, or it allows. The lateral design allows you to have that. So this is the bidirectional design. So you have two gates here instead of a drain. We call them source 1 or source 2, and it depends how you want to say it. These two gates, depending on how you use the biasing condition, they can provide you the 4-quadrant operation, and depending on how you control S1 and S2. But at the core of it, the device is very similar to a conventional GaN HEMT. And if you just draw a cut line, if you draw a cut line right here in the middle, you can see this almost looks like a conventional transistor. And this is part of the reason is that this region right in the middle is called virtual drain. And this virtual drain the electric field and the physics turn out in such a way that it gives you this advantage of 1.3 to 1.5x. So this is something that we studied with TCAD simulations, and this is what I'm showing here, that if you take a conventional transistor, what happens is that your electric field starts to decay after the end of the field plate. However, the presence of the field plates on the other side, like in this particular case, field plate number 4 and field plate number 2, what it allows you to do, it is allows you to keep your electric field a bit higher, and these field plates helps in spreading the electric field and allows you that sharing of the voltage on either side, a little bit of sharing. And this is why instead of getting a 2x penalty in the resistance, you are only getting like 50% penalty or 40%, 60%, depending on how you design your device. But it's not like you have to have the spacing which is equivalent to 2 transistors blocking in either direction. So this is the key advantage. So what we have done is we have made these transistors in our research group. I think about 1.5 years back. We wanted to see this transistors in action. So we tried to fabricate the first set on GaN on silicon, because that's what is very common. And we saw in the literature that this is what people had done. So this is the transistor structure, very standard. We just took a standard GaN on silicon HEMT epitaxial material. We deposited silicon nitride, and we did all these etchings to get these field plate in place to get the advantage, to get the breakdown voltage. So so basically, when we fabricated it looks like a bidirectional device. If you would see on the bottom, I have the output IV curves, output IV curve here, where you can see it's symmetric in first and third quadrant. Nominally, the on resistance is similar. There is minor variation, but again, this is within error range. And when we tested the off-state performance of these transistors, they both blocked in either direction. We were able to get around 1200, 1300 volt in both direction. And on the same transistor, because this is catastrophic breakdown after 1300 volt, I'm showing here in this yellow curve that you can sweep the same device 400 volts in either direction, and it will hold. So we obtained around 1360 volt breakdown in this, and we were able to get that for 10 micron of LGD with a low on resistance of 10 ohm millimeter. And I think I don't have the data pointed out here. I'm realizing it, but we were able to get somewhere on the lines of around close to 1600 volt on on GaN on silicon transistor. And after that, we started running into buffer breakdown, or vertical breakdown instead of lateral breakdown in these devices. So very reasonable numbers that we were able to get for these devices on GaN on silicon. And of course, this breakdown numbers were obtained with optimization. It wasn't as trivial. So one of the things that we noticed, and we tried to see that what helps in achieving this breakdown for 10 micron of gate to gate spacing, somewhere close to 10 micron gate to gate spacing. So what we found out was there was a particular field plate design that helps. And for that, basically we had a whole array of different field plate 1, field plate 2 design, and one has to take into account the fact that there might be some alignment errors. But what we saw was if we had our field plates slightly on the shorter side, it helped in managing the peak fields better. And we saw something similar with the TCAD simulations as well. So nothing too out of the ordinary that we got, and these numbers were comparable with state of the art. So once we did that, we realized that, of course, we are limited by silicon buffer breakdown. And of course, if we want to make a real device out of it, we need a lot of margin, so on and so forth. So scaling the voltage beyond 600 to 900 volt is obviously going to be very difficult. One of the solutions that we thought was, why don't we switch to sapphire substrate? Because now sapphire, you will get slightly lower dislocation density, and sapphire is insulating material, so the vertical breakdown may not be an issue, and we can push the breakdown voltage to higher voltages. One of the key questions, and which I was very interested in, and that's why I wanted to move to higher voltage to see how this sharing is affected. Basically, at 600, 1200, around these volt range, and I think if we look at other reports, nominally it's somewhere around 50% extra resistance that we were seeing, give or take few tens of percentage, but somewhere around that there is some advantage. So the question that I asked myself is that if I go to a higher voltage with GaN HEMTs, with GaN bidirectional devices, that does the ratio move towards better sharing, or it makes it worse? And how does it compare to unidirectional transistors? So this is something I was very interested in, and to see like how far can this be pushed before other challenges start to happen in these devices. So we went ahead and we fabricated devices on sapphire. So this was homegrown material where we had iron doped gallium nitride on sapphire. We deposited AlGaN GaN, nothing too fancy, very similar 2000 ohm, 2000 mobility material, close to 300 to 400 ohm per square sheet resistance channel. So very standard D mode transistor. So we fabricated this device, and again, you can see that the bidirectional performance is there. It's symmetric across first and third quadrant. We were able to get reasonably low on resistance, and this is what we expect, right? Nothing too out of the ordinary. Basically, for 40 micron gate-to-gate spacing, this is written LGD, but it's gate-to-gate spacing. We were able to get 3 kilovolt breakdown, and as you can see, the device is not like catastrophically broken yet. This is due to the tool limits. So somewhere around that we are seeing it, and if you would just do a simple math, you would see that the field is reasonable. We are getting like somewhere around 0.7 to 1. 0.75 megavolt per centimeter, around that number. So this is something that we would expect. If the field plate design is decent, we can get close to 1 megavolt per centimeter from GaN lateral devices. So currently we are working on pushing this even higher, and what we are trying to do is to see what is the field that we can get out of in these devices. So right now the on resistance that we got was 20 millimeter, which was pretty good. And if we translate this number, it turns out to be close to 10 to 12 milliohm centimeter square, depending on how we account for active area in these devices. And very similar to our GaN on silicon results, we do see similar trend that the field plate design that we saw for 600 volt devices, the same learnings that we have learned, they translated even here as well. And of course, once we can measure beyond 3 kilovolt, the results will become more apparent. So this is one of the highest breakdown voltage transistor for bidirectional devices that is available at the moment. And of course, with 3 kilovolt, it helps to expand this to 1200 volt or 1700 volt applications as well. The on resistance was quite good. We got somewhere close to 10 milliohm centimeter square, so which is quite a good number for gallium nitride transistors going close to 3 kilovolt. We also started doing some pulsed and preliminary dynamic results. Due to the limitation of the tool, we were only able to apply up to 40 volts. So this what you are seeing here is the off-state stress, or the quiescent point was set up to 40 volts, and the pulse width limitation also came from the instrument. Currently, we are in the process of upgrading our instrument so that we can go up to 3 kilovolt in off-state stress and basically get some sense of dynamic performance from these devices. And the fact that the degradation is not significant, it also tells us that our field plates are doing a reasonable job. We are probably not using surface straps for spreading the field in these devices, but again, we need to go close to 600 volt or 1200 volt in the off-state pulsed IV or dynamic on resistance measurements to get a better sense of where we are. So, so just to kind of provide you with a summary, that we started to look at the conventional transistors, like and this is from literature. We did a literature survey to see where those transistors were. So if I look at like going from 650 volt to 6500 volt, I see that especially for as we are going deeper into higher voltage devices, the gap is reducing, and this is something obviously we need to understand a little bit more, that why that is the case, or how how that on resistance is turning out to be reasonably close to what we are seeing here. But again, it makes for an interesting study that if we keep on pushing the voltage, maybe the shared region between the two sides can be maximized, and the extra resistance penalty may not be as bad as we think it is. And obviously, I do understand from the perspective, this is from the perspective of a more academic or fundamental demonstration. And once we start to do some dynamic on resistance measurement, there might be some hysteresis related challenges, but this is more from a fundamental standpoint, that what are the limitations and how electric fields manifest themselves in the device, so that you can at least try to get the upper bound of performance for these transistors. So this is something, what are we doing now, or what do we plan to do moving forward? So moving forward, one of the things is to fabricate like high current and high voltage transistors, and I'll speak about it in a few minutes. The idea is that can we extend the breakdown to 10 kilovolt, and this is something I'm very interested in doing, is to perform extensive dynamic on resistance study to really understand how the space between these two designs, or the voltage sharing region, gets impacted if you are sweeping one side versus other side, high voltage, how hysteresis manifest themselves, and how does silicon nitride holds at the surface in the bulk region. So it's something that we are intending to do in the near future. Concurrently, what we are working on is we are starting to work on this, is to look at circuit topologies and solutions, basically to demonstrate the advantage of bidirectional GaN FETs. And for this work, possibly we are looking for like samples from industry. Currently, we are executing NDAs with a couple of companies to get parts and to get more information, so that we can start to build some circuit solutions to see and demonstrate the efficiency advantages that these transistors bring into play. And also, we hope that by working on circuit level solutions, it will give us some insights into how to design our device better, and basically overall serve the full pipeline of from applications down to circuits to devices and to materials. And something that we are working on at the moment, and I can't share a lot of details because this is not published at the moment. And we are also looking at like, can we think of a fundamental device design change compared to the field plate design, which allows, nominally speaking, for a high voltage device, a unidirectional and bidirectional, to exhibit the same on resistance? Like, at the fundamental level, can we call effectively the drain as the second gate, and basically take the advantage of the gate-to-gate spacing to the maximum possible way. So this is something that we are working on at the moment. Hopefully, we'll have some publications in the near future. So with that, let me dive into the next part of our efforts. So as I said, we are very interested in demonstrating high current and high voltage, and I want to clarify what high current means for me. So we universities in general are very good at proof of concept transistor, testing out new ideas, but the transistors that we make are small. They don't give enough current. Like the currents are in tens of milliamps range at 1 volt. Typically, I would say they are 1,000 to 10,000 or 100 to 10,000 times lower in current value that you can see in product data sheets there. And of course, since they are fabricated in academic clean rooms, not really rugged, we can't expect them to survive for 10 years. They would fail rather quickly. So at some level, the transistors that we fabricate technically cannot be utilized by circuit designers. And this is something we are looking into it so that to test some of the things which are not commercially available. And when I look at the GaN HEMT current ratings, so this is like transform. This is a picture taken some time back from when transform was transformed. Basically, if I look at the current values, these are extremely high. The lowest current that I found on the website was where the transistor was rated was 3 amps. And these transistors do not fail easily. And for circuit designers, at least few amps of current is needed to design something productive. So this is something we are doing at the moment, is to see if we can scale our devices to at least make these transistors good enough to be tested at some level. So we started with a single finger device. I would like you to see here. So single finger device means it's truly a single finger device, 100 micron gate width, one finger. And now what we are looking at is this multi-finger design, or multiple devices connected in series to connected in parallel to give us the current value that we may need for high current applications. So that's what we are doing. So to highlight this, basically, we are able to nominally maintain the same current density. There is some drop that we are working to figure out, but the good thing is that as we are scaling, the current is boosting. We are not seeing a huge change in gate leakage. Nominally, the properties are maintained. So in terms of off state, the off state is, again, you would see between 1 finger and 10 finger is nominally similar. So what we were trying to see is how far can we push these devices in our academic clean room at UW, in a research clean room at UW-Madison. So far we have placed some effort, and we have gotten close to like 100 finger devices, and this 100 finger device can give us like few amps of current at 1 volt. With sustained efforts, we have been able to make sure that the yield does not go to hell, because otherwise it's again extremely challenging to fabricate these devices. So we are in the process of basically trying to make these devices, test them so that we can do some dynamic on resistance testing, which is again difficult to do on a smaller device with low current device due to n number of parasitics issues. So all in all, we are at that point where we can fabricate few amps of devices, and our hope is to take this learning and apply this to bidirectional transistors and get more insights into the device operation and mechanism. So with that, I would like to switch gears and talk a little bit about the ultra-wide bandgap aluminum gallium nitride channel transistors that we have been working on. And here we are collaborating with Dr. Asif Khan and Professor Pasai. So why we are interested in that is because just like wide bandgap were the next gen compared to silicon, compared to gallium nitride and silicon carbide, these are considered next gen materials. There are a lot of different materials that you can choose. Aluminum nitride is there, gallium oxide is there, diamond. Our choice is aluminum nitride, partly because there is a substrate available that has high thermal conductivity for power electronics. Thermal conductivity is extremely important. These days now we can get, or we are very close to getting 4-inch native substrates, which is great. aluminum nitride offer very high critical field, and even if we take alloys of aluminum nitride, like high composition aluminum gallium nitride, we can get the advantage of high critical field. We can get heterojunctions in these devices. So all in all, at least in my opinion, it makes for a very good power electronics device. And another thing is, now that the world is more familiar with gallium nitride HEMTs in the last 2 decades, this is almost like a big brother of gallium nitride, where a lot of those things that we have learned about GaN are similar, and in the same spirit, a lot of things are unique and different. So let me try to dive into what kind of transistor structure that we are working on. So on the left, you will see it's almost like an analog of GaN transistors that you have seen. So where you have a barrier layer, which is aluminum gallium nitride, and you have a channel, which is gallium nitride. So in principle, you can think of this very similar design. However, the challenge is these are wide bandgap materials, and unfortunately, the metals that we have, their work functions are very limited to the metals that are available to us. So making ohmic contact, which is not that challenging in gallium nitride, at least now, is still extremely challenging in these ultra wide bandgap materials. So ohmic contact, we don't think about it too much when we are thinking of on resistance breakdown voltage, but in these ultra wide bandgap, it's something that cannot be taken lightly. So in order to facilitate ohmic contacts, what we do is we add this reverse grade AlGaN layer. The whole idea is basically to give a slightly lower bandgap material so that the metal can form a decent ohmic contact, and then you want to make sure that this layer is connected to the barrier and through the channel in order for the electrons to flow from source to drain. So this is something that other groups have looked at it as well, and it seems like this is one of the ways to facilitate an ohmic contact. And still there is a lot of effort that is being put on this to lower the contact resistance. Still the contact resistance is extremely high and non-trivial to make ohmic contacts, and it requires a bit of material and device engineering both to give you low resistance ohmic contacts. So recently we have gotten reasonably low contact resistance, somewhere close to 2 ohm millimeter with these. So that work is under review at the moment. So hopefully that will be available soon. So what we have done is we have really tried to dig deeper into this design, basically to look at like how this design can be tuned to give what we want. So we have studied the buffer design. Depending on what kind of buffer you have, if you carefully design your buffer, control the alloy composition well, then it can give you a little bit of boost in mobility. You can see it's going from 140 to 155, not a significant boost. But overall, in your sheet resistance, which is what you care about from a conductivity viewpoint, you do get some advantage if you design your buffer carefully. One of the reasons why mobility doesn't change that much is because instead of gallium nitride, we are using AlGaN channel, and AlGaN is an alloy. So you get alloy disorder scattering. And in our experience, what we have done so far, it tells us it's very hard to solve that problem unless you can make an alloy grow or deposit an ordered alloy. And this is something we'll look at in the near future. So the other variable is channel design, channel thickness, and we can see that, like, depending on if you look at the band diagram of this, the channel thickness, ideally you want to make it as big as you can make it, because it relieves some of the E field in your channel. It gives you low sheet resistance, decent mobility. However, the channel has to also you also want your channel to grow pseudomorphically on the substrate. And since there is some lattice mismatch between the channel, which is less than 70% AlGaN versus aluminum nitride, so there is a certain limit to which you can deposit the channel thickness. And this is what we were able to do. We were able to deposit without introducing too many new defects, 280 nanometer of channel with optimizations, and we got somewhere close to 3600 as the sheet resistance. So another optimization that we looked at was to look at the aluminum nitride interlayer. In gallium nitride, design, aluminum nitride is extremely important. This interlayer, it makes a huge difference in mobility. However, you'll see here the mobility difference is only 10%, and this is probably because the channel is in an alloy instead of a binary material. But all in all, you can see that we were able to still reduce our sheet resistance close to 3000 ohm per square. This is again very close to state-of-the-art results that are out there, and this is roughly 10 times more than gallium nitride sheet resistance. But the idea is that these materials, they have high breakdown field, and with high breakdown field, they would ideally compensate for the reduction in mobility or reduction in conductivity. So all in all, with on resistance and breakdown, which is Balika figure of merit, you would see an overall win in these designs. And that is something that needs to be demonstrated at the moment. So the key material learnings that we have had so far is that alloy disorder scattering is really hard to get rid of. We basically need to make sure that we optimize our channel deposition to the best possible way to give us the highest possible mobility in these layers. So now, once our material was ready, we started to look at transistor results. And when we looked at literature, we saw that majority of the reports were less than 1 kilovolt. There were very few reports that were above 1.5 kilovolt. And majority of them were not passivated. And as we know from gallium nitride experience, that if you don't passivate your device, you can overstate the breakdown voltage in your transistor because of the presence of surface traps. The other thing that we also noticed that the on resistance was very, very high. Like even for ultra wide bandgap material with higher sheet resistance, the on resistance was significant. So this is something we decided to explore for AlGaN channel to see what we can do. So we looked at a 60% or 65% AlGaN channel in order to take the most advantage of high breakdown field that can possibly be obtained. We used what is called a reverse grade layer, going from 87% barrier to 30%. We etched it down. We made this design, which is very similar to what you are familiar with in GaN transistors. And what we were able to achieve was 3 kilovolt breakdown with 64% AlGaN channel transistors, and we got around 80 ohm millimeters. So the on resistance is a bit high if you are used to seeing on resistance for gallium nitride transistors. And this is again because the conductivity is 10 times lower compared to GaN channels in these AlGaN channels. And one of the key things to note here is that these devices were measured before silicon nitride passivation. So this is right after Schottky gate deposition. We measured it, and we saw somewhere on the lines of 3 kilovolt, but this is without passivation. So after that, we did passivation and we did field plate. And you can see that we saw a lower breakdown. We went from 3 kilovolt to 2 kilovolt. We went from 1950 to 1710 and 1380 to 1290. So basically, we saw a reduction in the breakdown voltage, and this is what tells us that probably the surface states at the surface were helping in providing some field plate kind of effect for these transistors. So after that, we again did the dynamic on resistance measurements after field plate to just see whether field plate was doing its job. And it seems like we have some current collapse, but all in all, it wasn't as significant as like 50-60% of current collapse. So nominally, we are seeing that the field plates are doing a decent job. Obviously, we need to measure them at higher voltage to truly understand the dynamic on resistance and basically the suitability of field plate, whether the SIN passivation and field plates are doing its job in reducing the electron trapping to a minimum. So this is something we are looking into it. So if we look at this work roughly, we see that with the gate drain spacing, we are seeing a change in the breakdown voltage. When we compare our work with others, we are nominally where everyone else is. The unpassivated results, ideally, they are not very useful because with unpassivated structure, current collapse is huge in these 3 nitride transistors. So with passivation around 2 kilovolt, we have somewhere close to 80 ohm millimeter. Very recently, we have improved those numbers significantly. But one of the key things I want to highlight here is that few things that are still lacking in the ultra wide bandgap space is where we still need to demonstrate high breakdown voltage with high electric field. And when I say high electric field, I'm not talking about like 10 megavolt per centimeter or 8 megavolt per centimeter. Just crossing gallium nitride or silicon carbide, basically 3 megavolt per centimeter with like 2 kilovolts of breakdown voltage, that itself has proven challenging in lateral devices, in GaN and even gallium oxide based lateral devices. So there is still a need to demonstrate superior on resistance breakdown voltage trade-off. And one of the key things is to enhance our fundamental understanding of how do we go from there. Getting close to 1.5 megavolt is not that challenging. We were able to achieve it rather easily, and other folks as well. However, pushing that number to higher E field is proving to be non-trivial, especially if you want to go to 1.5, 2 kilovolt, 2.5, 3 kilovolt. So less than 1 kilovolt, it's a different ball game where you can achieve high field, but once you start to cross 1.5 megavolt, we haven't seen enough work. So in this regard, our group has been working on this problem for about a year now, and very recently we were able to get close to 2.5, 3 kilovolt breakdown with 2.5 to 3 megavolt per centimeter in a lateral device. So basically, like to make it simple to understand, like roughly 10 micron of source drain spacing in this ultra wide bandgap transistors, they can hold about close to 3 kilovolt. So we are in the process of understanding these results and publishing them. So hopefully you'll see it soon. So the last thing I would say and end my presentation with this statement that ultra wide bandgap, with all its great material properties, it's on its way to demonstrate its critical advantages, especially over wide bandgap material. So as a researcher and as a person who likes to see power semiconductor devices, to me these are exciting times ahead and a lot of opportunities that will come with it once we push the performance beyond these wide bandgap devices. So thank you very much for listening. If there are any questions, I'll be happy to answer those. Thanks again.
Thank you, Dr. Gupta. So we do have some questions. The first one is, in unidirectional GaN high electron mobility transistor, substrates are typically tied to the source. How do you handle the substrate in the bidirectional GaN high electron mobility transistor?
So in our case, we kept, I think if we kept our substrate, when we were dealing with silicon substrate, we kept our substrate floating. And in sapphire, since the substrate is insulating, I believe there was no real need to bias the substrate.
Okay, thank you. The next question came in through chat. Is your 10,000 square feet clean room a user facility that is open to outside users?
Yes, so it's open for anyone who would like to use. It's very similar to the clean rooms that are available in the country all around. So yes, anyone can use it by paying a user fee, and it can be accessible. Yeah.
Thank you. The third question is on the Q&A. Says, thanks for the presentation. Do you estimate the thermal resistance of the device using sapphire substrate considering its poor thermal conductivity? Can this be used for high power?
Well, I would imagine using sapphire would be challenging, especially for high power. The way I think about this is that sapphire, the reason why we are doing it on sapphire, not on silicon carbide, is just because we are more familiar with sapphire, and sapphire is cheaper to do. But So if thermal conductivity is a concern and you really want to use gallium nitride for high voltage application, one possible solution is to use GaN on silicon carbide, because then you can take advantage of silicon carbide thermal conductivity and go to high current, high voltage applications. Of course, there is the trade-off of cost of sapphire versus silicon carbide. But considering sapphire poor thermal conductivity, either you have to come up with a clever solution where you somehow lift off the GaN materials, or GaN, like once the device is fabricated, you thin down the sapphire, maybe through substrate vias. Like you have to think of a clever solution to solve this thermal issue. But like just like normal GaN on sapphire may give a lot of challenges if you were to use them for high current, high voltage applications. I would imagine so.
Thank you. The next one is from the chat. What are the advantages and relative cost of the sapphire substrate compared to silicon?
As far as I know, and this is more hearsay that I've heard, like there is not a huge difference between sapphire and silicon cost, especially for 6-inch. Like, okay, when I say it, I should mention that like when we take the cost of fabrication of a wafer, let's say if silicon is, I'm just making up random numbers, but let's say if silicon is, let's say $25 for a 6-inch wafer, and your GaN growth and fabrication is roughly around $1,000, then sapphire is like $60. So basically, even though the sapphire substrate is expensive than silicon, but in the scheme of things, when you have to grow the material on top and then you have to fabricate that wafer, the overall cost of the sapphire substrate is not as significant. For example, if you were to go to silicon carbide, then compared to the growth and fabrication cost, the substrate cost will become important and something that cannot be ignored easily. So that's how I look at it, that nominally speaking, going from silicon to sapphire for a 6-inch wafer may not be that big of a cost hit.
Okay. Thank you. The next question. Why sapphire substrate doesn't need to be biased? Won't everyone use it if it was that easy? Everyone, including TI, Infineon, Navitas, etc., seem to have patterns on substrate biasing. Also, please comment on why biasing is required.
So I think, at least as far as my understanding goes, the idea behind biasing is where you would have some conductivity. So as far as my understanding goes, in sapphire, since sapphire is an insulating substrate, and then on top of that, you grow an insulating buffer, and then you have your conductive layers. I find it hard to imagine that how would you even bias the substrate, and what would you bias the substrate to, because it's an insulating material. Obviously, not to say that this is an elegant solution. So obviously, there are a lot of reports out there in the literature where people have done floating silicon and with bias silicon. But I think in silicon, in silicon, it makes a little bit of sense, because when you deposit gallium nitride material, there may be, due to the growth processes, it makes the surface, I think the silicon substrate surface, a bit conducting. So therefore, the biasing makes a little bit more sense in silicon compared to gallium nitride, as far as I know. And for floating and substrate grounding, it's at least in my opinion, it's complex, and I think this is something that goes beyond like DC performance. This is something where we have to look at dynamic performance, electron trapping in the off state, and see the impact. So it goes more into, I would call it like more reliability sort of domain, rather than like just proof of concept demonstrations where it doesn't show a significant difference. But like just from looking at the literature on GaN HEMTs, you do see a difference between keeping your substrate floating versus biasing it. And I think it seems like a lot of people do prefer biasing the silicon substrate. On the other hand, on sapphire, the challenge that I personally see is that, like, how would you bias an insulating substrate? It won't make sense. So there, even if you want to bias it, you end up with a floating substrate, and then you have to see and run test and basically make sure that the floating substrate doesn't create huge reliability challenges.
Thank you. The next question, could you introduce the Wisconsin Chips Center to potential industrial partners?
So yes, I can I can provide a very brief overview of. So recently we have at Wisconsin, we have started about, I think, a year back or somewhere around that, where we have now concentrated efforts in semiconductor area under one umbrella across the whole university. And under this Wisconsin Chips, basically what we have done is we have taken all the stakeholders who are working on different aspects of semiconductors, and it could be materials, it could be devices, it could be circuits, it could be, quantum. So all under one umbrella, where we have identified the strengths of our university in this space, and what we call them as pillars. So we have 6 different pillars, where one of the pillars is wide bandgap and ultra wide bandgap materials and devices. Another one is circuit design EDA. Another one is thermal photonics. So I would encourage everyone to check out Wisconsin Chips. And if you see there are some opportunities for collaboration, we'll be more than happy to welcome you and give you an overview, and looking forward to have a chat with you.
Thank you. Next question. For sapphire-based bidirectional device, what is the thickness of sapphire substrate?
So these devices, we are using the standard sapphire that we have been using. So we didn't pay any special attention to it. So these are grown on a 2-inch wafer. So we use roughly close to 430 micron thick sapphire that we are using. But again, as I said, these are more from a fundamental study viewpoint. But if you would like to use them for real application, you may want to thin it or start with slightly thinner sapphire substrate.
Thank you. So the next question has 3 parts, so we will go ahead and answer each part. The first one is, okay, they say, great presentation. I presume the multi-finger devices presented were unidirectional.
Correct.
How do the multi-finger bidirectional high electron mobility transistors perform?
So we haven't fabricated those at the moment yet. We are still in the process of optimizing the multi-finger unidirectional devices. This is something that we are hoping to start very soon, the multi-finger bidirectional devices. As now we have some decent breakdown voltage on these devices. Our focus was more on pushing the breakdown voltage a little bit higher, and now that we have done that, this is something we are going to start very soon. The multi-finger design to push the currents higher, and hopefully this will allow us to study some dynamic properties in a little bit better way than just on wafer probing.
Okay. And the second question is, would there be follow-up study on the capacitance of the bidirectional high electron mobility transistors?
Yes, I think overall, in general, we are very interested in truly understanding and enhancing our understanding, as well as community's understanding of bidirectional transistors. So this is another reason why we want to go to like these scaled finger designs, so that the capacitance of our device is significant enough so that it can be measured by the instruments. Because currently, if you are using a single finger device, the capacitance is so low that all the noise and parasitic capacitances does not allow the study of change of capacitance with applied voltage. And this is something we are very interested in seeing how those profiles look. But again, to do that, we need good enough area so that the capacitance numbers are in tens of picofarads, so that it can be measured easily with the instruments that we have. But if there are more sensitive instruments out there, we'll be happy to collaborate with people and ship samples if there is any interest from anyone.
Okay, and the third part is, would the passivation deposition method and integration location in the process flow for the ultra-wide band gap AlGaN high electron mobility transistors influence the relatively poorer performance?
It's a possibility. So this is something again, we are starting to look into that. But it seems like the answer would be yes and no. At one level, I do feel that there are opportunities to improve the passivation. But when I look at the literature and look at like the efforts of a lot of different research groups, it seems like it's a challenge that the whole community is facing. So it seems like while it may be a problem, but there are other fundamental challenges at play which are not like as obvious. I would imagine passivation may be one of the challenges, but it's not the challenge. At least that's what it feels like from our early investigation.
Thank you. From next attendee, any comments on GaN caveats, which is a current aperture vertical electron transistors, which have two DG in a vertical GaN on GaN structure for bidirectional devices?
At least as far as my understanding goes, first of all, like for a vertical, and this is more of a comment on the vertical geometry versus lateral geometry. I believe the voltage sharing that is possible in lateral geometry may not be trivial to achieve in a vertical geometry by default, because I think if we look at silicon carbide results for bidirectional transistors, it does seem like the on resistance sharing is very limited, because in some ways these are more like two different transistors fabricated in the same process flow on the same die. As far as, again, I may be mistaken here, but I have yet to see any fundamental change in the device design or basically electric field sharing beyond what people have been doing for unidirectional transistors. That tells me that there is some critical advantage that is left, that you can take from vertical transistors. And if we are talking about a normal cavity with a two-dimensional electron gas channel, I think the challenge lies in the drift region, because the drift region on both directions, it's not trivial to block voltage with the same drift region. And I think therein lies the bottleneck of vertical transistors for voltage sharing. So you probably will need that drift region on both sides to hold the voltage. However, in a lateral region, just because of the geometry, it allows you to share part of that drift region on both sides. And this is why I feel laterally, there is a chance of a better performance compared to a vertical counterpart. Obviously, the lateral and vertical differences are always going to be there. But as far as my understanding goes, I don't know if in vertical, if it's as easy as lateral to do voltage sharing. And that's why the advantage is possible in lateral devices compared to vertical devices. And I'm assuming you are talking about a normal cavity where the channel only lies in the two-dimensional gas. So, but the problem lies in the drift region and the voltage holding region, not the channel region.
Thank you. So we'll take one more last question over the time now. As for passivation, what are the passivation options can be used that gives both high breakdown voltage and low current collapse?
That's a very good question, and it's currently very like we are looking into it. So I won't be able to share like some of the leading thoughts that we have, which might be helpful. But I would imagine like if we go back and look at the nitrides area, silicon nitride has served us well, and I think obviously silicon nitride is a very good starting point because it can help basically we can do similar things as we have done in gallium nitride to apply to aluminum gallium nitride channel transistors. But what we have to also start thinking is silicon nitride the best passivation material, not just from a material compatibility perspective, but also from like electrostatics perspective. So this is something we are thinking about it at the moment and trying to explore and see, is there a better option? But based on everything that we have done so far today, we don't have a better solution than the usual suspect like aluminum oxide, silicon nitride, silicon oxide. We haven't seen anything that has been game changing for those, but we are looking into exploring different options to see if those materials can provide the passivation capability as well as give some other advantages that might help in pushing the electric field to higher. But all the numbers that you have seen in my presentation, they are all done with PECVD silicon nitride, very standard, nothing too fancy.
Okay. Thank you, Dr. Gupta. So with that, we will end the webinar for today. If anyone has more questions, you all can email directly to Dr. Gupta. Thank you for attending.
Please feel free to reach out if you have questions or any comments. Me and my students will always be happy to hear thoughts. And if you have just comments about technology in general, welcome to hear those. It will help shape our research and make things more productive for everyone. Thank you for the opportunity.
Thank you.
All right, thank you. Bye.